So I want to talk about something called separable degree of an extension, because this will be crucial in some counting arguments in proving the fundamental theorem of Galois theory. So I'll remind you the definition of separability. You have a field F, you fixed an algebraic closure F bar, take an algebraic extension, and you always assume that the algebraic extension K lives inside F bar. Take an element A in K. You say that an element of F bar is a conjugate of A if it shares the same minimal polynomial. So if Px is the minimal polynomial of A, some other root of that minimal polynomial will be called a conjugate of A. These are like the brothers of A. They share the same minimal polynomial. So if A has a minimal polynomial of degree D, then A has at most D brothers, D conjugates. You say that A is a separable element if it has actually D conjugates, meaning it has the most number of conjugates as possible. In other words, if the minimal polynomial has all distinct roots. We say that our extension is separable if every element of K is separable over F. And we have seen that in characteristic 0, all algebraic extensions are separable. But there are, in characteristic P, situations where this might not hold. Okay. So I want to define something called separable degree, which right now would seem something completely different, but it would get linked very quickly. So let K over F be an extension, and a finite extension, let's say. That would be good enough for us. And then let K colon F S, this will be called the separable degree of the extension, be the number of embeddings sigma from K to the algebraic closure fixing F pointwise, such that sigma restricted to F is identity. We have looked at these things before. You have some algebraic extension. If you fix an algebraic closure, you can always embed it inside the algebraic closure. I'm looking at the number of these sigmas. The first result is, and the proof of this lemma shows what this concept has to do with the notion of separability. If you take a simple extension is a technical word, I think I never used it. It's the extensions that are obtained by adding one algebraic element, extensions like this, that we studied right in the beginning. Let K equal to Fa be a algebraic extension of F, and let's take the minimal polynomial of A. So then K is Fx mod the minimal polynomial. Right. So a standard thing. Then there exists a bijection between the embeddings of K into F bar, such that sigma restricted to F equal to identity, the things that count this separable degree, and the conjugates of A. The point is that if you take this extension that is obtained by adding one algebraic element, And now if you want to embed this in the algebraic closure, you have no freedom of what to do on F. This restriction to F has to be just identity. You cannot touch the elements of F. So all you have to decide is where to send A. And we said this time and again before already, in the previous discussion of splitting fields already, all that you can do is send A to some other root of this minimal polynomial. Because wherever A goes, this guy would satisfy still the same polynomial. P of sigma of A would be 0 for any sigma such that sigma restricted to F is identity. So each sigma A, each of these sigma A's are conjugates. And conversely, if you give me a conjugate of A, then I can send A to that conjugate and get an embedding. Conversely, given any conjugate of A in F bar, conjugate, let's say A prime, there exists an unique embedding sigma from K to F bar such that sigma restricted to F is identity and sigma sends A to this A prime. This was essentially what we kept calling our embedding lemma. Yeah. That when you take these embeddings into algebraic closure, you can send A to one of its brothers, to one of its conjugates. So the number of conjugates is same as the number of these embeddings. Okay. So consequence of that's the proof of this lemma. So the consequence of that, or maybe you should call it corollary, is that the separable degree of this extension is the number of conjugates of A. On the other hand, the degree of the extension, you would remember, is equal to the degree of the minimal polynomial. Right? Because the extension, after all, is fx, since fa is, after all, fx mod p. Yeah. So that shows you, and we know that the number of conjugates is at most equal to the degree, and equality holds if and only if the extension is separable. So what we find is, for at least these kind of very simple extensions, what are called simple extensions, the separable degree is always less than or equal to the actual degree, and equality holds if and only if A is separable. Okay. Maybe this is the corollary. So this gives you essentially another way to compute the degree by computing the number of these embeddings, at least in the separable situation. So in characteristic 0, for example, the number of the degree of the extension you find is equal to the number of these embeddings, which seems like a rather abstract thing, but it would become useful. And the theorem that we want to state, not prove completely, is that this statement that we have here for this kind of extension, fa over f, actually holds for any algebraic extension. So let any finite extension, otherwise we cannot count, of course. So let k over f be a finite extension then the separable degree is always less than or equal to the actual degree of the extension, and equality holds if and only if the extension is separable. So when the extension is separable, then there is no difference between the separable degree and the degree. This is all you need to remember. There are some other facts that are rather nice about this separable degree. It's also multiplicative in towers. So if you have a tower like this, the separable degree of the whole thing is the product of the separable degree of the upper extension times the separable degree of the lower extension. And then you have theorems like the big extension is separable if and only if the smaller extensions are separable. But we wouldn't bother about it. We'll be happy stating the fundamental theorem of Galois theory for finite extensions in characteristic 0, and there everything is separable, so we are fine. But the proof of this theorem, this one here, is just a straightforward induction using the corollary up here. So we know this theorem when the extension is obtained by adding one element. And for general elements, you can just choose a sub-extension by adding one element and then induct. So let me just explain with a picture. So what do I want to prove? Let's prove the inequality. So you have K, so here's the proof of theorem, sketch. You have K, F, choose a thing not in F, take this extension in between. So this is some proper extension because A was not in F, so I actually gone up a little bit. So this degree up here is less than the degree of the big extension. Okay. And then here, I know that the separable degree is less than or equal to the actual degree. And up here, I know that this holds by induction on degree of extension. So assume that the result holds for all extensions whose degrees are strictly less than the degree of K over F. Then by induction, you know that this holds, and then you know this holds, and then since the separable degree and the degree are multiplicative in towers, both sides are multiplicative in towers. We know that the degree is multiplicative in towers. I just stated that the separable degree is multiplicative in towers. It's actually a reasonably easy exercise. It follows. When you multiply left-hand side, you get the separable degree of this. When you multiply the right-hand side, you get the degree. Yeah. And then if you had equality, then you would get equality. So the equality holds if and only if it's separable. That also follows from the same corollary using exactly a similar induction. Equality in separable case is a similar induction. Okay. And that's basically what we'll be interested in. When we are in separable situation, the number of these embeddings equal the degree of the extension.